Hey everyone, on this lesson we are going to solve the problem 3 on the section of mathematical problems. So this problem 3 says write and implement a predicate with the name of Totient phi that calculates and computes the value of the Euler's Totient function phi for the argument m. So here the idea is that this is basically a predicate that computes the Totient function and we calculate the value for the arguments. So here we are passing the argument m and we get that phi, the corresponding value on this function to the argument equal to 10 is 4. So before going through the implementation of this predicate, we need to first understand this function Totient phi and see what this function does. So for those who don't know, the Euler's Totient function in number theory, it counts the positive integers up to a given integer m that are coprime to this value m. So on previous problems we saw how to compute if a number is prime. We also saw how to compute the greatest common divisor of two integer numbers. And we define now that two numbers are coprime if their greatest common divisor is 1. So if we have two numbers and their greatest common divisor is 1, it means that these two numbers are coprime by definition. So what we do in this Euler's Totient function is to count how many positive integers up to a given value n are coprime to this value. Let's see an example. What if the argument m is 9? Well, we have to count how many numbers from 1 to 9 are coprime to 9. We can see that, for instance, 1 and 9, they are coprime because the greatest common divisor between 1 and 9 is 1. In the same way, 2 and 9, they are coprime because the greatest common divisor between 2 and 9 is 1. In the same way, 4, 5, and 7, right? They are all coprime between 9. So here, as we can see, they are all relatively prime. Another known name for coprime is also relatively prime. If you see the notation relatively prime, this means the same as coprime. So as we can see, these numbers are coprime to 9. But as we can see, the other three numbers that exist between 1 and 9 on this range, that is the numbers 3, 6, and 9, they are not coprime with 9. Why are not they coprime? Well, because the greatest common divisor between 3 and 9 is not 1. In fact, it is 3. In the same way, the greatest common divisor between 6 and 9 is not 1. It is 3. And finally, the greatest common divisor between 9 and 9 is also not 1, it is 9. So as we can see, if we have that the greatest common divisor is not 1, then they are not coprime and they are not relatively prime. So if we count how many numbers are coprime in this range, we see that we have 1, 2, 3, 4, 5, 6. So in total, what is the output of this function when the value m is 9? Well, 6, because there are 6 numbers between 1 and 9 that are coprime with 9. Now you can already see and intuitively that here, if we have a value m and we compute the greatest common divisor between m and m, this greatest common divisor will always be m. It will never be 1. So it is trivial to see that if you have two numbers and the two numbers are the same, the greatest common divisor between the two is the same number, right? So basically when you compute the range from 1 to m will never be included in this list. So let's study a last example to understand this. We have now that the value m is 10. So between the range from 1 to 10, we need to count how many numbers are coprime with 10. On the list, we only see that 1, 3, 7, and 9 are coprime with 10. The rest of them, for instance, 2, 4, 6, 5, and 8, they are not coprime with 10. So since these numbers are relatively prime, or which is the same, coprime with 10, we count how many we have. We have a total of 4 elements. So the value for the Totient function when m is 10 is 4. So the value of phi is 4. That's why what we see here on the example, if we calculate when the m is 10, the value on the output phi is 4. Finally, it is important to note, and it should be mentioned, the special case, and this is a base case. What if our argument is 1? Well, if the value of m is 1, we need to count how many numbers between 1 and 1 are coprime with 1. And in this case, this is the only case that the greatest common divisor between two numbers is 1, if the numbers are the same. And this is the case where both of the numbers is 1, right? If you compute the greatest common divisor between 1 and 1, this is 1. So in other words, 1 is coprime with 1. That's why the value of phi, when the m is 1, we only have one number, which is 1. Very well, so once we have understood this Euler's Totient function, let's start with the implementation to this problem. So we have created now a new Prolog file. The name of this file is Totient.pl. And now let's first make a brief description of this predicate. So remember, you can make comments in Prolog with the % symbol. So here the name of the predicate is Totient phi. We have two arguments, m is the input, phi is the output. So as we can see, phi is the output value in the Euler's Totient function when the input is m. Right? This is the predicate that we will work on. So here let's first start with the base case. Since we will define this predicate in a recursive way in Prolog, the base case is when the m is 1. When the value m is 1, then the value phi on the output is 1. So here we can just establish the base case, Totient phi. If the m is 1, then the value of the output phi is also 1. And this is the first fact that we define. This is the base case. Base case, m is equal to 1, right? So now let's take a look at the recursive case, as this is where we have the most important work of this predicate. So here we have an argument m that is greater than 1, right? And then we have the output, which is phi. So basically what we have to do, by definition of the Euler's Totient function, is to count how many elements from 1 to this value m are coprime with m. So to do this, we will define a auxiliary predicate. Let's just call it T for Totient phi. This is the auxiliary predicate that we will define. This predicate will receive also the first two arguments, but we will also have two extra arguments. The first extra argument is the first element in the range that we want to find coprime numbers. In this sense, remember that if we have a value m, we need to check all the values from 1 until m. So here, 1 is where we start. This is our starting point, right? Now, the second extra argument is going to be how many coprime numbers we find within a subrange. So at the end, when we have that our subrange is the same as the original range, in the sense from 1 to m, then phi is going to be equal to this argument. So at the initial point, how many coprimes have we found? Well, initially we have not found any prime yet, right? Any coprime numbers yet. So initially this is 0. So now let's define this predicate here, the t phi predicate. And first let's describe this predicate, and what we will have here is m, we will have phi, we'll also have the initial value of the range, which is k, and c. So here the idea is that we count on the range from k until the value m. So here we have this interval, right? So first of all, what is the base case for this predicate? Well, what if we have reached the case, we have applied many times this predicate in a recursive way, and we have reached the case that phi, right, is what we want to calculate, and here the case that we have reached is that the first initial value of the range is the same as the last one. So what if we have this case in here? What if the value k, which is the starting point, is the same as m? Well, if the starting point is the same as the final point, this means that we have completely looked over all the subranges. So on this case, the value phi for the solution is going to be the same as the value c. So it is also going to be phi. And if we find this case, we can apply the cut operator to just stop here the backtracking Prolog process, so we will not go below. Remember that this cut operator works like a wall, like a vertical bar, and it basically means if you satisfy this condition, this is basically representing that you will not go below, you will just finish the backtracking process. If this is not satisfied, if this is not met, then we have the other case, and this is the recursive cases that we may have. So now we have that here we have the argument m, we have the solution phi, we have k, we have c, right? So here what we have to do, if we have a range like this and we know that k is different from m, because what if k is the same as m? Well, if k was the same as m, we will have this case, this will be satisfied, we will reach the cut operator and we will stop. So if we come here, we know for sure that m is different from k. Now, some students usually ask, and they say, well, can you have the solution done, or basically the program, without the cut operator? And the answer is yes, you could have that. But if you don't use the cut operator here and you just leave it like this, then here you will have to verify that these two values are different. First of all, you need to compare, you need to have a condition here. So if you have to do this, this is far more inefficient than not have to do that. So we will always prefer to use the cut operator. So the program is very and far more efficient than not using the cut operator. We gain efficiency and the time execution for this program is less. So we need to verify, since they are different, that k is less than m, right? Because if k is greater than m, then we cannot do anything, since k is the starting point. And now we need to verify if k and m are coprime. So we need to some sort verify if k and m, they are coprime to each other. So this is a predicate that we will program now. Before continuing this rule and the body of this rule, we need to define a way of having the coprime numbers. So when two numbers are coprime, well, we saw by definition that two numbers are coprime with each other if their greatest common divisor is 1. So we can very easily implement the predicate coprime. We have two numbers x and y, and these two numbers will be coprime if and only if the greatest common divisor of x and y is 1, right? And remember that this predicate, the greatest common divisor, is a predicate that we have already programmed before on the previous lesson, right? On the problem 2, we implemented this greatest common divisor predicate. So let's just copy the solution to the previous problem. If you haven't watched the previous problem, then you can just assist and see how we define this predicate of the greatest common divisor. So we already have the predicate that given two numbers, it returns true if they are coprime or false if they are not coprime. So what if they are coprime? Well, if these two numbers, right, the first in the range and the value m that we want to compare of the coprime numbers, if they are coprime, it means that this counter that we have, we need to increment. So we will define a new variable, which is nothing more than c plus 1. So what we are doing, we are incrementing the counting of coprime numbers, right? And once we have implemented the counter, what do we have to do? Well, we have to verify if the next number, k plus 1, is also coprime with m. And we need to do this sequentially, right? So here we will just define a new variable, which is k plus 1. And this is going to be the new range, and the new initial value of the Totient phi function. So on the next invocation, we will have this range from k1 to m. So the last thing that remains to do is to have the recursive invocation of Totient phi, like so, again with the same arguments. These arguments will never change. But now the initial value that we will check is not k, but k1, because we already checked this value. And we will also increment the value of the counting for c1. Now, very important, we only increment the value of c, the value of the counting, if these two numbers are coprime. If they are not coprime, we shall not increment this. So we can use here a cut operator that basically says, okay, if they are coprime, if these two numbers are coprime, then we will have here a wall, a vertical bar, right, that says, okay, if they are coprime, we have reached the cut operator and we will apply this body and we will not go below, okay, because now we will have a case that they are not coprime. So let's just put it here, like so. We will have the same case on the arguments, but now they will not be coprime to each other in here. So in the same way, k is less than m. We first start by verifying this. And note this, now we ask the student, and this is by far the most interesting part of this problem. Do we have to verify if the two numbers are not coprime? So in other words, do we need to write this, not coprime k and m? Because we just said that this is the case that k and m are coprime. And this is the case that k and m are not coprime. So do we need to verify if this happens? And the answer is no. We do not need to write this. And the reason is because we are using the cut operator. We are using this operator. And this operator means if they are coprime, we will reach the wall and we will apply this body and we will not go below. So we will not execute this code because we have the cut operator. If you don't use the cut operator, then yes, you need to write this. You need to verify that they are not coprime. So this is the case that they are not coprime, right? So if you use the cut operator, again, it's something that you gain efficiency because you don't need to do this comparison, neither this comparison in here. Because if they're coprime, you will not go to check this clause. Okay, the Prolog backtracking process will not try to unify the clause. It will basically stop. It will execute this and it will stop, right? Now, if this is false, then we will not reach this, so that we will execute this other code here, which is the case that they are coprime. So here we can also make a comment. Case k and m are coprime, right? And this is the case. Let's put it here. Case k and m are not coprime, right? So if they are not coprime, the only thing that we need to do here is to increase the range, right? We also already checked that they are not coprime, so we only need to check with the next number, which is k plus 1. So we don't increment the counting in here, very important, okay? This counting, which is the last argument, is not incremented here because they are not coprime. So we shall not include, okay? We must not include this value k on the counting list for coprime numbers. If they are coprime, then yes, we include k on the list and we count plus 1, right? If they are not coprime, then we don't include this value k on the list of coprime numbers. So again, finally, we have the recursive invocation of t phi m phi. Now, again, then the next value is k1, so we just write k1. But now, the counting variable is not modified, it's the same. It remains the same because the same value we had before. We have not incremented nothing because they are not coprime, right? So it should be clear that this is the case that they are coprime, k and m, and we increment the value of the counting, and this is the case that they are not coprime, so m and k, since they are not coprime, we do not increment the value for the counting when we start on the next range. So we keep doing this over and over. We keep incrementing the value of k, so we keep incrementing the range until where or until when? Where we keep doing this until we reach the case that k is not less than m. In other words, k is exactly m. So if we have reached the m value for the k, it means that we have this case. And the solution phi is going to be precisely the value of the counting, right? That we had here. So here's the base case that we only reach when we finish the range K to Bm, right? So this is why the auxiliary predicate T phi is very important, because we partition the range on one side and we also partition the counting of the coprime numbers. Finally, remember to always end the facts and the rules of your Prolog clauses with a final period, right? And with this, we finish the implementation of this problem 3. We remind that you can check this code and download it on the downloadable documents of this lesson. So finally, let's verify that this is working right. Let's start with the example. Let's apply the Totient phi on the argument m is equal to 10 and verify that this is 4 on the output. So first of all, we open the Prolog environment, the SWI Prolog console. So now we load the file. In our case, the name of our file is Totient, right? You just here type the name of your file. We press enter. So this returns true. It means that we have no errors in the compilation. We have loaded all the predicates that we have written on this file. So now let's start verifying the function Totient phi, and we verify this predicate when the value of m is equal to 10. So here we have that m is 10 and phi is the output. So this should return 4. We press enter and we see that this is 4 precisely. Let's check for the case where m is 9. So here we apply Totient phi. Now m is 9. This is phi. Let's see now the value of phi. This should be 6, right? As we can see, this is also 6. You can also test your own examples. For instance, what if the value is 102 and this is phi? We see that we have a total of 32 numbers between 1 and 102 that are coprime with 802. In the same way, you can calculate Totient phi of 356. And here we can remember that this is an output variable. You can name this variable as you want. You can also name it to be, for instance, b. Okay, there's no obligation in using the name phi. So here, let's just see. So we have a total of 876 numbers between the range of 1 and 356 that are coprime with this number 356. Very well, so with this we finish the solution to this problem 3. Remember that you can download the solution to this problem as well as the problem statement on the downloadable documents of this lesson. See you in the next lesson.